Hey everyone, welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. Now, I am recording this show on Monday, May the 10th, 2021. So again, all kinds of really interesting things could happen in the upcoming week that I am not prepared for and will not be covering during this show, but I will cover it next week. But if you want to join live, ask your question to me, go ahead, sign up, join my YouTube channel every Monday, 5 p.m. Pacific time, and I'll answer your questions and do follow-up answers and all kinds of stuff. So definitely join us. All right, let's get into the questions. Earn expected. What would the sky look like on a planet close to the center of the Milky Way? Right, so here out in the suburbs of the Milky Way where we live, the stars are about 4 light years apart on average. And that's what we see with the closest star to us is like Alpha Centauri, which is just shy of 4 light years. But as you get closer and closer to the center of the Milky Way, the stars get closer and closer apart until they're an average of like a light year apart. It's sort of, you have a similar situation in globular clusters where the stars are really close on average apart. Now, the intense radiation that's going on from all those stars makes it a not very habitable place. And so astronomers think that in fact, the center of the Milky Way isn't very habitable because of all that radiation. And astronomers also think the outskirts of the Milky Way aren't very habitable because there's just a lack of the heavier metals that are required to create terrestrial planets, sort of in that in-between zone where probably you've got habitable planets. But let's just say that there was some planet that was able to survive all of that radiation and life was able to form and be able to sit there and look out. Yeah, you would see a sky that was filled with bright stars. Many, many, many more. I mean, we've only got 10 stars within 10 light years of us. But if the stars were like a light year apart, you would have, and I kind of can't do the math in my head, but you would have, magnitudes more stars in the sky. And so you would have this like bright night sky all the time. There's a great book called Nightfalls written by Isaac Asimov that talks about this idea of this planetary system that has multiple stars. And so the people on this planetary system have never experienced darkness at night. And finally, there's like this time when all of the stars are over the horizon and there's this eclipse and people freak out because it's dark. So it wouldn't quite be that. You would definitely have day and night, but you would have a night sky that is just jam-packed with stars. People always ask me if there was places you could go in the Milky Way to just sort of see what it would be like standing on a planet that is close to the center of the Milky Way or standing on a planet that's in a globular cluster and seeing a night sky with multiple number of really bright stars all the time would be kind of amazing. The other thing is that depending on how close you are to the supermassive black hole at the heart of the Milky Way, you're going to see these stars moving fairly rapidly from year to year. So in our case, the stars in the sky they don't even move. Like you have to wait tens of thousands of years to see significant movement of the stars. You can measure the movement, but for us to really appreciate them. And yet, if you were at the center of the Milky Way, the stars would be whipping around. And so you would, over a lifetime, notice a significant change in position of some of the stars that are close by. Again, depending on how close you are to the center of the Milky Way. So yeah, it would be pretty amazing. Matthew Nebel. Will Rocket Lab's Neutron rocket be able to compete with Falcon 9? Is there any reason a paying customer would choose Neutron? I think there's lots of opportunities for rockets to compete with the Falcon 9 at this point. Still, you've got rockets that are very reliable, things like some of the stuff from United Launch Alliance. You've got stuff where you've got, the European launches, etc. Rocket Lab is really trying to go after the smaller launch market, the small sat stuff that's in the multiple hundreds of kilograms. The Neutron is that next stage up rocket. So it'll all be, depending on how they differentiate themselves from what SpaceX is doing with the Falcon 9. But the reality is that SpaceX has already mostly planned to abandon the Falcon 9, abandon the Falcon Heavy, and move on to the Starship. And that's where future rocket companies are going to have a really difficult time competing with what Starship does, assuming they can make these things come back from low Earth orbit. Because I've mentioned this several times in the past, that the double whammy with Starship is that it's fully reusable. And so it actually makes it a very inexpensive rocket to launch and maintain. And so weirdly, the most powerful rocket that will be possible on Earth, the one capable of launching 150 metric tons into low Earth orbit, will also be the cheapest to fly. Will only be the cost of replacing the fuel. And so you're looking at an order of magnitude less in terms of launch costs. So I think that Rocket Lab with their Neutron, which is the follow-on, it's the bigger version of their Electron. They're hoping to make it more reusable. But it's all in the same bucket. You've got all these other launch companies. They're all having to deal with the elephant in the room, which is Starship. And up until this point, Starship has been kind of hilarious, right? They fly and they explode on the launch pad. That's what they do. But now one landed and it didn't blow up, much to everyone's surprise, possibly even Elon Musk's surprise. And so I think at this point, we're looking at an attempt at an orbital flight later on this year. Elon Musk is still saying that they're going to be seeing Starships head off possibly to Mars in 2024, not with any people on board, but still that original schedule is still possibly part of the works. And so how do you compete with that? I've mentioned this on previous episodes that if you haven't dropped everything and tried to figure out fully reusable rockets like Starship, you could very well end up being completely cut out of the market. And in fact, the only company so far that I've seen that is actually seriously investing in this, there's like a Chinese aerospace firm announced last week that they're going to be producing their own full two-stage. Essentially, it's a copy of Starship. And they drew it, they showed us a render of what it's going to look like. That's it. That's the only company that I've even seen say that they are even contemplating what Starship is going to be doing. So I think unless somebody, and I guess it made like nobody's willing to take the risk to say, okay, fine, what Elon Musk is planning and Starship is planning, or SpaceX is planning, is serious. They're all going to just be caught without a market. Sean Marson. Does every star have its own Oort cloud? Do we know anything about the contents, dimensions of other stars' clouds? Do they vary with the size of the star? Thanks. Of course, the tricky thing with Oort clouds is that we aren't entirely sure that the sun has an Oort cloud, that our solar system has an Oort cloud. The Oort cloud is this spherical cloud of comets that's theorized to be out there surrounding the solar system. And it's theorized because it's gigantic. It stretches out like 2 light years away from the sun, pretty much halfway to the nearest star system. So in theory, these stars, if they all have Oort clouds, they overlap one another. And the only way that we know that we have an Oort cloud is that we have comets that fall into the inner solar system. And when you measure the orbit of these comets, they appear to be on some gigantic orbit that takes them past the sun and then all the way out to 20,000, 50,000 astronomical units away from the sun. As you can measure this orbit. If you see enough of them, and they all seem to come in many different directions, you make the assumption that there is this vast cloud of icy material out in the outer solar system. But they're so far away, we can't measure them directly. We just measure them when they're falling in. So to not be able to measure them when they're close, it's really tricky to try and measure them around some other star system. Now, the assumption is that they're there. And of course, with, say, Comet Borisov that came through, an interstellar comet, clearly comets are being generated in other star systems and making their way into the solar system. Now, that said, Kuiper belts have been detected in other star systems. So the Kuiper belt is this other belt of icy material that's closer in to the sun. And so it's warmed up a little bit compared to the Oort cloud, and it's more dense, and the occasional vast icy ring has been detected in an exoplanetary system. So it's probably going to be a while before we actually have like direct evidence that there is an Oort cloud surrounding the sun, not to mention finding one around. It's only when things are colliding with each other, heating up, do we actually get any kind of like direct evidence that they're out there. Strange quark star. Do you think Elon Musk's promise of getting the cost of a trip for colonization down to that of a small house is realistic? And if so, at what timescale? Sure. Yeah, I think it's realistic to get to the point that you can send a human being to Mars for a few $100,000 when you sort of imagine if they're going to put 200 people on each Starship, and when you multiply that by multiple hundreds of thousands of dollars per person, you're in the billions range. So it's a realistic amount of money. The question is like, what's there waiting for people when they get to Mars? It's like you could book a one-way trip to Antarctica right now for, say, $5,000. Maybe you could fly down to Argentina and then book a trip on a boat, some icebreaker, and then go down to Antarctica, and then you could just not get back on your boat and live in Antarctica for as long as you can. So it's not about the getting there. It's about the having the infrastructure there to support your existence while you're there. And that part, I think, is going to cost more than a couple of $100,000 per person to be able to support that. We're looking at millions of dollars and decades to get to the point that we'll even have enough infrastructure to support a fairly small science station of astronauts that are permanently on the surface of Mars. But give it decades, give it hundreds of years, and eventually more and more people will be going to Mars for various purposes, and eventually we'll be living on Mars. Escape MCP. Fraser, what's the next cool space thing happening that you're excited about? JWST? Anything sooner? Nice dig at my Canadian accent. Escape MCP. Yeah, listen, I mean, it's funny. The ones that I was most excited about have recently just happened. So we had the Perseverance arrival at Mars. We had the Ingenuity helicopter doing its flights. We had the launch and landing of a Starship, which was pretty great. But there's a lot of big things still happening over the course of the year. Now, you did pick the big one, which is the launch of the James Webb Space Telescope on October 31st, 2021. It will launch. I think the other thing that I'm most excited, I don't know if it's going to happen this year or it's going to happen into next year, and that's going to be first light for the Vera Rubin Observatory, which is, of course, this giant 8.4 meter telescope that's going to be scanning the entire night sky every few days, and will show us just how the universe changes from night to night in ways that we never expected. It's going to find comets and asteroids. Maybe it'll find Planet 9. It's going to find supernovae. And then it's going to find stuff that we didn't even know were out there, which is going to be exciting. I think to sort of follow on with Starship, of course, if Starship does its next launch and actually is able to make it to orbit over the course of this year, that will be the one. Like Starship going to orbit, returning to Earth, landing safely. That will be the biggest, most eventful moment in a decade of space exploration. More? I'd say those are the big ones for me. Dragon King. Do you believe in microbial life in the universe? So for people who've watched my channel for a while, I've been on the record many times that I am of the opinion that there probably isn't any life in the universe. That's just my opinion, man. Don't yell at me. And I mostly form that opinion because the Fermi paradox just baffles me, and I can't imagine why we don't have alien robot factories building von Neumann probes all over the solar system right now. But, people keep bringing new arguments for the Fermi paradox at me. I'm happy to keep taking the arguments. But there's this idea that while complex life might be really, really rare in the universe, microbial life, bacteria, etc., might be very common, and that one of the explanations for why life is so rare is that it's this transition from microbial life to complex life, multicellular life, is actually very difficult. So from what we can tell, multicellular life has only happened once here on Earth. We look around, we don't see lots of examples of animals coming together from multiple cells, plants, things like that. We just see everyone is related to this one common ancestor. And so that tells you that it must be rare because it didn't happen a lot. So then the question is, are there single cellular organisms, bacteria across the universe? And, a lot of astrobiologists feel pretty confident that yes, the answer is yes, that we will find microbial life. We'll find it on Mars. We'll find it on Europa. We'll find it across the universe. I'm less convinced about that. And that's just because it's sort of amazing what kinds of emergent behavior even single cellular organisms can do given enough members. You look at like slime molds that are able to, although I don't know if slime molds are single cellular anyway, but you can see how collections of ants can form a very complicated behavior across the entire colony. And so even if you have lots of single cellular organisms collected together into this vast colony of bacteria, you can imagine more complex emergent behavior coming together. Maybe there could be technology. And so it feels like that's not we have a very Earth-centric perspective on what is the difference between a single cell and a multicellular creature. And so you would think that the universe would come up with more complicated, weirder, creative solutions to the kinds of problems that we face. And so I'm like, okay, so where are the von Neumann probes sent by the single cellular organism colonies that we don't see? So, my feeling is that we won't even find microbial life anywhere else in the universe. But that's just my opinion, man. More questions in a second, but first I'd like to thank our patrons: Hal Roseman, Adam Scoose, Eric Mowry, Andrew Planet, and the rest of our 830 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. HQ Cart. How far is Earth from the Big Bang? Can we spot the Big Bang location? So we get this question a lot, and the big problem, of course, the Big Bang problem, of course, is that when we imagine the Big Bang, we're imagining this explosion, expanding with wreckage of space material, and it all started in one little spot, and then it's just this kaboom, and it's exploding and expanding away from each other. But that's not what the Big Bang is. I come back to this question because I'm trying to sort of come up with an explanation that really will center in people's minds. So the one that I've used the most is imagine a grid in 3 dimensions. It just goes on forever. Up, down, left, right, all dimensions. It's just a grid, right? Like graph paper, but in 3 dimensions. And then you make the length of all of the lines in between the points in the grid longer. And so the boxes, the cubes that are forming in this grid just get bigger. And so if you're at a galaxy that's on one part of one box in this grid, and someone else is in a galaxy that's another box in this grid, and as the grid expands, that looks like that galaxy is moving away from you. And no matter where you go, if you're on the other side of that grid, if you're on a different box, everywhere you look, everything seems to be moving away from you. And so it's not an explosion. It's an expansion of space. And the one possibility is that the universe, even back at the beginning, was infinite. And so this grid just went on forever in all directions. Just that the gaps in the grid were very, very tiny. But then over time, they got bigger and bigger apart. The other possibility is that the universe is finite, but then it just wraps like a 3-dimensional game of asteroids. You go out the top and you appear on the bottom, you go at the front, you appear in the back. So either imagine a 3-dimensional game of asteroids, which I know is kind of hard to do, or imagine that just this grid just goes on forever. It was infinite at the moment of the Big Bang, and it's still infinite. It's just that the size of the grid, the boxes in the grid are getting bigger. I don't know if that helps. So we can't spot the location because the location was everywhere. That every part of space, where you're standing, where I'm standing, Andromeda, everything was all part of the Big Bang. The Big Bang was everywhere, all at the same time. Sergio Botero. Why was the Sun-Earth L2 point chosen for James Webb instead of positioning the telescope at geostationary orbit such that it would always be eclipsed by Earth? The Hubble Space Telescope is in low Earth orbit around the Earth. And that gives you a bunch of advantages: very quick communication time. You can fly up and service the Hubble Space Telescope, but it gives a bunch of disadvantages. One of which is that the Earth is in the way of half of the sky that you want to see. The other problem is that as you fly around the Earth, you go into the sun and then out of the sun. So you're heated up and you're in darkness. These are problems. And so when NASA was trying to figure out where they were going to put the James Webb Space Telescope, because it's an infrared observatory, they needed to put it in a place that is very stable and can observe the sky and always keep the sun in the exact same spot of the sky. And so they chose the L2 Lagrange point. And so the Lagrange point is this gravitationally stable place that is sort of the interaction between the gravity of the sun and the Earth. One Lagrange point is in between the Earth and the sun, and there's a lot of spacecraft that are put there. The L2 point is on the far side of the Earth. So it goes sun, Earth, L2. And so by positioning the telescope there and putting the sun shield directly sort of facing the Earth and facing the sun, you've got the three brightest objects in the sky. You've got the sun, the Earth, and the moon, and they're all blocked from your point of view of the telescope. And the telescope is kept in shade by this giant sun shield. And so if you put the James Webb in a geostationary orbit, then you're going to have some combination. Sometimes the Earth and the moon are going to be in your way. Sometimes the sun's going to be in your way. And you're constantly going to be having to shift James Webb to try and keep that sun shield in front of the hottest, brightest objects in the sky so that you can keep it cool. But if you go out to L2, you can just block everything you need. Now, you're not actually going to be in the shadow of the Earth when you're out at L2. L2 is a fairly large region that you're going to be orbiting around within, but you're going to be able to keep all of the bright light pollution to one spot that you cover with the sun shield, and then you don't have to look at it. Kyle Hunt, does SpaceX need NASA to achieve its goals? NASA is SpaceX's biggest customer. And right at the very beginning, when SpaceX was running out of money, NASA was the company that signed up, or organization that signed up for rocket launches and really helped fund the development of SpaceX. Like, SpaceX would not exist if it wasn't for NASA and those early contracts. And then they helped with other follow-on contracts with the Cargo Dragon, with the Crew Dragon, and all of the various missions that have been launched on SpaceX rockets. So SpaceX wouldn't exist without NASA. And then as SpaceX has been transitioning to the Starship, NASA has been providing technology in terms of like on-orbit refueling. They've also, we just saw in the last couple of weeks that they've announced that they're going to be choosing the SpaceX Starship as the lander for the Artemis mission, although that's gotten a little bit snarled up in the courts. So we'll find out what happens in the end with that. So the two are kind of inextricably tied together. And at the same time, NASA isn't like designing and building the rockets that SpaceX is doing. They're paying for flights. They're paying for flights to space, which is kind of amazing. So at this point, like if NASA fired SpaceX, would SpaceX go out of business? No. I think at this point, SpaceX has got enough customers, it's got enough momentum with what it's doing that it would be able to continue on and keep growing. But it's weird to me that people always seem to position it like somehow SpaceX and NASA have some kind of antagonistic relationship when they really don't. SpaceX is offering NASA an inexpensive, reliable way to get astronauts to space, which is a capability that they don't have since they no longer build the space shuttle. And it's actually cheaper than flying astronauts on Russian Soyuz rockets. So there's no antagonized relationship between the two of them. If anything, it's funny. You talk to people who are working on missions for like space telescopes and things like that, and they often will try to push NASA to go with a SpaceX solution like the Falcon Heavy. Because if you get, for a Falcon Heavy, you can launch for $90 million. With Falcon 9, you can launch for $60 million. Like NASA's test mission went on a Falcon 9. for a fraction of the price. Like the whole mission was just a few $100 million, including the launch costs. And so to have a launch provider that is half the price, that gives you double the mission. So no, in no way, shape, or form do SpaceX and NASA have any problems with each other. They are they're quite a partnership, and hopefully that will continue on for decades to come. Now, SpaceX is going to do its own thing, but NASA will always be there as a customer to pay for flights to go to space, which I think is perfect. Arjun, would Starlinks be brighter if they were lower to the ground? So the problem with Starlinks, like when a Starlink goes overhead, if it's reached its final operational altitude, you're not able to see it with your unaided eye. If you had a pair of binoculars and you knew where to look, you'd be able to see a Starlink passing overhead. The problem, of course, is when the Starlinks pass through the CCD of a telescope that's trying to do science. And so astronomers trying to view a galaxy, and you get this Starlink pass right through, and there goes that data. But the Starlinks are actually only visible when they're illuminated in the sky when it's nighttime. And so that's only a problem right after sunset and before sunrise, when you've got this gap. That's sort of the time that you can mostly see satellites. And then as the rotation of the Earth carries you into the shadow of the Earth, then you can no longer see the satellites overhead. And it's the same thing. And so in fact, the number of Starlinks that observatories are going to be able to see depend on their latitude. If you're close to the equator, then you actually don't see a lot of satellites, because essentially the satellites go into the shadow very quickly. But if you're really high to the north or really far to the south, like in Chile, then the Starlinks make a fairly long trail. And in some cases, they're there for the entire pass. They're essentially illuminated the entire time that they're flying overhead. And the higher you make that altitude, then the different latitudes, the lower latitudes that you have to go to be able to still see those entire passes. So say the OneWeb satellites, they fly at like 1,000 kilometers compared to the Starlinks, which fly at like 500 kilometers. And so the OneWebs are actually visible for their entire pass for many parts of the Earth. But because the satellite is farther away, it's less bright in the sky. And so you've always got this balance. And so yeah, if you flew your satellites at a much lower altitude, they would be vastly brighter. Like they would be, you'd see them down on the horizon, even with the unaided eye, but then they would zip into the shadow of the Earth a lot more quickly. And so it might be, and I'm really just spitballing here, but it might be that the solution is fly the satellites lower, because then you have less time that the satellite is illuminated in the sky. If you're just 200 kilometers up or 300 kilometers up, then maybe you're actually going to be able to mitigate the light pollution problem from the satellites. This is an idea that I'm kind of mulling around in my head, and maybe I'll talk to Casey later on this week about this. Just this idea that, in fact, it might make a lot of sense to fly our satellites lower, closer to the Earth. It's safer from a space junk problem. It's better from a communication standpoint. As long as you can have some kind of, say, air-breathing ion engine, or even just a very efficient propulsion system, maybe it makes the most sense to fly the satellites low as opposed to flying them really high. I really need to investigate this more deeply. So that's why I want to take that question. 6 Bob Ohms. NASA said one nuke won't stop an asteroid, but what about 1,000 nukes in waves? So the problem with shooting a nuclear weapon at an asteroid most of the time is that it won't do anything. They're an enormous amount of mass in an asteroid, even something that's fairly small. I mean, they're the mass of a mountain or more. And then to sort of worry about whether or not you can actually change the course of an asteroid using a nuclear weapon is laughable. The thing that you can do is that you can try to break up the asteroid. And so, for example, the thing we've really learned about is, say, some of these asteroids like Bennu or Ryugu, that they're actually just collections of debris held together by their mutual gravity. And so if you could blow them up with a nuclear weapon so that they scatter into this giant cloud, if you got enough time, then before, if you just had this one object or collection of objects that was going to hit the Earth in one location, now you've created this spray. Some of this is going to hit the Earth, some of it won't, because now it's more like a shotgun blast as it's going past Earth. So it all really depends on how much advance warning you've got, how much time in advance of when this thing is going to strike the Earth, you try to hit it with a nuclear weapon. You want to have it hit the surface and pretty much vaporize on the surface of the asteroid to then create a thrust in whatever direction you want. You don't want to sort of blow it up relatively nearby, but just in general, if you're trying to protect the Earth from an asteroid, time is the thing that's most important. The sooner you can take action, the more advance warning that you can get, the more orbits that you've got to work with, the less damage you have to do to it to try and shift its orbit to turn it from a dangerous asteroid into a safe asteroid. So really, early detection, like so many things, is the key. On Canada, can we make a telescope the size of the Earth's orbit? Yeah, we can. And it wouldn't be that difficult, but it wouldn't be a telescope as you probably are imagining it. So the technology that we want to look at is this idea of interferometry, that you can combine the light from multiple telescopes. If you have a telescope at the North Pole and you have a telescope at the South Pole, like we did sort of with the Event Horizon telescope, you can have those two telescopes observing an object at the same time. And instead of just having the combined light of the two dishes, as long as you can line up the wavelengths perfectly, they'll act like a telescope that is the size of the entire planet Earth. So it's as if you had telescope all in between that were filling up from the top of planet Earth to the bottom of planet Earth, one big telescope. And all you need is just those two telescopes, one at the top of the Earth, one at the bottom of the Earth, and that acts like a great big telescope. Now, what that allows you to do is it gives you resolution. So it allows you to essentially see, like, say you had a supermassive black hole that you were looking at, you would be able to resolve where the black hole's event horizon begins because it's so bright. But it doesn't give you light gathering power. So you still only get the light gathering capability of the combined light of the two telescopes, but you get that resolution because of their distance. And so you can scale this idea up. You could say we could put one radio observatory on one side of the Earth's orbit and one radio observatory on the other sides of the Earth's orbit. We could have them observe some object like a supermassive black hole or the heart of the Milky Way or some star or something like that, and they would be acting like a telescope that is the size of the entire Earth's orbit. But once again, you only get the resolution, you don't get the light gathering, you don't get the faintness ability of a telescope that's that big. Now, this only really works in the longest wavelengths of the spectrum, so it only really works in radio waves because, as I mentioned earlier on in this answer, you've got to line up these wavelengths to the individual wavelength. And so when you've got wavelengths that are centimeters long, meters long, it's relatively easy. You start a clock, you record, I record, we finish recording, we take our two sets of data, we merge them together on computer, line up the wavelengths perfectly, and then we get that really incredible image. But if you're trying to observe in a wavelength that is a lot smaller, like visible light, which is in the nanometers, then imagine, you've got millions of nanometers per meter, and you're trying to line up these two sets perfectly. It's impossible to do unless you're doing it in real time. Now, there are telescopes here on Earth that do visible interferometry. The European Southern Observatory's very large telescope is 4 separate telescopes, 8.4 meter telescopes that can act like one telescope. And the way they do this is they run a laser essentially from a signal from each of the 4 observatories, and then they have these lasers interfere with each other in a way that the pattern is perfect when the telescopes are perfectly aligned with each other in terms of distance. But to do that in space would be tricky. And so there are some ideas for telescopes that would be launched into space that would move at the perfect amount away from each other in space to the point that they're aligned so that they're seeing the sky at the exact same moment down to the wavelength, and then they would act like a telescope that is their separation. But imagine if you've got one on one side of the solar system, one on the other side, you're looking at like 15 minutes to communicate between those two telescopes. That would be really tricky to line them up. So I can imagine a future where we're building bigger and bigger interferometers in space. It'll start out in terms of radio waves, but I can sort of imagine you take 2 big telescopes, have them side by side, and they get themselves in perfect alignment, and then they slowly drift apart farther and farther and farther, but stay in alignment. Maybe you could sort of drift them out farther and just get more and more resolution as they expand away from each other. So stay tuned. I've reported on these kinds of ideas in the past, and I'm sure someone's going to crack this and we'll see something in space. A space-based interferometer, visible light, infrared, that would be incredible. All right, those are all the questions this week. Thank you, everyone who joined me for the live show, submitted your question. Thanks to everyone who asked questions in the chat and his comments on the various videos. I really appreciate it. If you want to join me live, I do this show every Monday at 5 p.m. Pacific time. So come on down and join me on the YouTube channel. All right, we'll see you next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free, and I write every word of it. Did you know that all my videos are also available in a handy audio podcast format, so you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.